This video will deal with pH calculations but with weak acids. The difference between a weak and a strong acid being that weak acids only partially dissociate. So we're dealing with an equilibrium, and as such we're going to have some equilibrium calculations in there. We'll make two assumptions in this calculation. We can see the first of them is that the concentration of the acid at equilibrium is the same as the initial concentration of the acid. So for a weak acid, for example, if you got some ethanoic acid and the concentration of the ethanoic acid in the bottle was 0.1 moles per decimeter cubed, you would take that to be its concentration at equilibrium, since the amount of dissociation is so small that the 0.1 moles per decimeter cubed won't vary significantly from that. The second assumption that we need to make is that at equilibrium these two things are the same. The reason why we can make that assumption, so if we turn our acid into a teddy bear, a badly drawn teddy bear, so when the teddy bear dissociates, so it has a really bad accident, then for each head we will have one body. So what that means is that the hydrogen ion concentration will be the same as the A- concentration. Sorry if the decapitation of the teddy bear offended you. Back to chemistry. So we have an equilibrium constant. This is the first time we've come across it. Very similar to Kc, but we're just giving it a different name because it's specifically to do with acid. So this is Ka. Remember that Kc was a measure of the concentration of the products over the concentration of the reactants, and it's the same here. So our Ka is the concentration of the hydrogen ions times the concentration of A-, so that's the rest of the acid, divided by the concentration of HA, which is our weak acid. Remember, we're saying that these two things are going to be the same. And if they're the same, then we can say that that's the hydrogen ion concentration squared over HA. So rearranging this, the hydrogen ion concentration squared is going to be Ka multiplied by the concentration of HA, so the hydrogen ion concentration is the square root of Ka multiplied by the concentration of the acid. And since pH is minus log of the hydrogen ion concentration, pH of a weak acid is minus log square root of Ka multiplied by concentration of the acid. Let's have a look at an example calculation. So we'll complete the Ka expression. So that's the concentration of hydrogen ions multiplied by the concentration of ethanoate ions divided by the concentration of the ethanoic acid, and if we assume that the hydrogen ions and the ethanoate ions are the same, then we can simplify that to this. Let's just have a look at the question and see what we know. Well, we've been given the acid dissociation constant for ethanoic acid. So that's 1.7 times 10 to the minus 5. And we've also been given the concentration of the ethanoic acid, which is that. And the question is asking for the pH of the ethanoic acid. And in order to get the pH of the ethanoic acid, first we need to get the hydrogen ion concentration. We'll just rearrange this. So the hydrogen ion concentration squared is Ka multiplied by the concentration of the ethanoic acid, which means the hydrogen ion concentration is the square root of Ka multiplied by the concentration of the ethanoic acid. Let's put the numbers in. So that's going to be the square root of 1.7 times 10 to the minus 5 multiplied by the concentration, which was 0.1, so that's going to be 1.7 times 10 to the minus 6, and we should have been getting 1.304 times 10 to the minus 3. Remember, that's the hydrogen ion concentration, and we need to get the pH, so we need to do minus log of the hydrogen ion concentration, so minus log of that last answer. So do that on your calculator. Remember, it needs to be to 2 decimal places, so we should be getting 2.88. Probably in the region that we'd expect for a weak acid, so probably in the 2s or 3s. Variation on this calculation. Here we're going to work out the concentration of the acid rather than working out the pH. So back to our Ka expression. Remember, we were saying that we can simplify to this, and we now want to make HA the subject of the equation. So with a little bit of rearrangement, we can get that. Remember, the pH will allow us to get the hydrogen ion concentration. In our example calculation, it's for methanoic acid. So methanoic acid is our carboxylic acid with just the one carbon, which will dissociate like so. So our Ka expression is that. Let's have a look at what we've been given and what we need to find out. So we've been given the Ka of the acid, and we've been given the pH. Now the pH means that we're going to be able to get to the hydrogen ion concentration, and since we're going to simplify our equation to this, if we know the pH and we know the hydrogen ion concentration, then the concentration of the methanoic acid is all that will be left. So we'll be simplifying it to that. We just now need to get the hydrogen ion concentration from the pH. Remember, hydrogen ion concentration is 10 to the minus pH, which is going to be 10 to the minus 2.2. Do that on your calculator. And I got 6.31 times 10 to the minus 3. So back to our expression. Now that hydrogen ion concentration needs to be squared. And then divided by our Ka, which was 3.6 times 10 to the minus 4. And if you've done everything right, then we're looking at 0.111 moles per decimetre cubed, and that's to 3 significant figures.